so what's the plan? Today we're going to cover what propping and needling actually is, what needs to be considered when we're looking at propping and needling. We will then run through some different types of propping and needling schemes with some examples of previous designs of mine and Richie's and across the business, with lots of case studies thrown in for good measure. And then, yes, like I said, we're going to have a worked example with Richie and then go to our live Q&A session. Okay, so what is propping and needling? What I'm going to talk about today is the temporary works associated with creating new openings in walls. And I usually see these schemes in the cut and carve demolition projects, like I mentioned earlier. The scope of work is just opening up an area which was previously a load-bearing wall. Because if the wall isn't load-bearing, then it doesn't need support. You just take the whole lot out from top to bottom. And hey presto, you've got your opening. Whereas if that wall is required to provide support to the structure above, then we need to provide some support in the interim while we remove a wall and an opening and put a new steel or concrete lintel in or whatever we're putting in there. A couple of examples of some typical scopes are shown here. What we have is an existing load-bearing wall that can be of any construction. It's typically masonry or concrete. And the scope is to open the wall up, but we need to understand what this wall is doing in the first place and the loadings that it is currently supporting. So it can be supported in the short term. But why can't we just knock the wall down and just whack a beam in quickly? Well, the reason for that is the beam is usually installed to support the structure above. So this structure could include a wall or floors or beams or roof or arches or anything like that. And the typical loading triangle onto that beam is shown here. This is a loading schematic of a lintel. So all the loading within the 45-degree load zone is taken by the lintel or the beam. And in addition to this, half or any point load or distributed load within that 60-degree zone is then also carried by that lintel. And this could be a window opening or a floor or a roof, for example. And so an extract from a very handy piece of literature, Fiona Cobb's Structural Engineer's Pocketbook, which I think every engineer should have a copy of this. It's really great. And I've put an extract in there. So you can see that all the loading from the floor and the wall within the 45-degree zone is taken fully, and then half of any applied load, but not including the wall self-weight, is taken into account too. But this comes with quite an important caveat, and that is it relies on the wall above arching over the opening. So masonry is able to arch even though it's just kind of a flat soffit or an opening. The masonry will arch around. And it's important to understand that for larger openings or openings where there's not enough masonry around the support areas to enable this mechanism, then this method doesn't apply. This 45-degree zone doesn't apply, okay? And it's worth noting that this is because the arch effect that we have in that masonry is for smaller openings or where we've got enough masonry either side to kind of take that arching load, like buttresses or abutments of an arch structure. That's why when you've got very small openings for services or ducts, you're not going to require any support at all. But when you start to go over something like ½ a meter or something, you're going to need some kind of support just to maintain support to that opening and prevent any loose brickwork from dropping through. Okay, so let's look at the type of things that need to be considered when we are propping and needling. The importance of site investigation. That is absolutely critical. And it's really important that we know what the structure is and how it's currently behaving so that we can predict what it's going to do. And it comes down to, yes, we're only less than 20 minutes into the presentation, ladies and gentlemen, but I'm going to say it, and it's GIGO. It's my favorite phrase, I'm afraid. And it's garbage in and garbage out. If the idea of the solution is based on garbage, then the solution itself is also going to be a load of garbage. Proper site investigation is required, and a little thought and money spent at this stage will really make for a much better solution. Okay, next point, lateral stability. Before the wall is removed, the lateral stability of the propping and the floor itself will need to be considered, yes. Support of other structures and not just the wall in question. So don't forget that adjacent floors may will need to be supported to remove the live load from the wall and just to reduce the amount of loading on your propping and needling. Yeah, that needs to be taken into account. Next one, okay. So the whole sequence of construction and not just the propping, that's important as well, for a couple of reasons, really. So the very first being that the loading of the temporary works. So the system needs to be designed for the worst case loadings. And therefore, if the structure is going to be loaded by plant or materials or some kind of storage, snow, potential vehicle strikes during its design life and not just, at the time of installation, then this needs to be considered at the design stage. So the other is to do with load history. And this is a phenomena that will include how to put the loading back into the permanent work structure once the propping has done its job. So two important things about sequence there. We need to understand the whole life cycle and also how that structure is going to behave in terms of its load history. Next one is what the permanent works is and what that's going to look like. So if we plan in advance, it may be that we can incorporate the temporary works into the permanent works and make a very slick and efficient solution. That's something that should be considered in the first instance. Are there any services in the wall or nearby that need to be considered? Any exclusion zones of note? The foundations of the propping. This is important as settlement under prop foundations will lead to an unsuitable support system to the wall. There is always a risk of movement and cracking, even though it's often just very small cracking. But there's always a risk of that. And so having foundations of the props onto some softer ground is just going to exacerbate that situation. How will the new permanent works be installed and how, and what is the plan for that? Are they using genie lifts? And if so, are they going to be able to put the beam in with the props at certain centers? Is the beam a really long one? And so it's very difficult to get installed into a small room, and will we need to splice it? These are things we need to consider. The allowable deflection in the structure during the works, there will be some movement as I've discussed, but how much is too much? That needs to be understood at the forefront. The loadings that must be considered. So are they all coming from above, or are they point loadings or evenly distributed? And then the overall stability of the structure. Who is taking responsibility for that? Also, what about the sequence of other openings being made and the interface between them? A propping and needling scheme that's just focused on one single opening and the responsibility of that engineer or responsibility of their scope is just that opening is different to the responsibility of the whole structure with, a dozen or more holes in very important structural areas. We need to make sure that overall, all these holes that we're putting in the structure, that is safe and it's not going to lead to a kind of a global stability issue. And then finally, we need to ask ourselves that is this solution buildable? It's really important that the design from both the permanent works and the temporary works is buildable and suitably mitigates risk using that ERIC principle of eliminate, reduce, inform, and control. Openings in load-bearing structures, they can go seriously wrong if not carried out correctly. So the overall solution must be safe and the sequence of construction must be practical and be able to do it on site safely. So let's use this example to explore some of those points. I've illustrated here the current loadings that will be acting on this wall. So we've got the green ones, which are vertical loadings from the wall above. This could be floors that are loading the wall above and then being transferred down, including the roof above. And it's in the guise of a couple of point loads because there's a services opening there. We've also got a couple of loadings to the right-hand side where we've got thrust from an arch, and we've got vertical load coming down, which is one of the spine walls on there. So let's take it through our list. We've got site investigation. We're looking for wall thicknesses. layout of the structure, including floor spans and floor to ceiling heights, floor construction, so we know and understand what the load is. What's the floor made out of, and will it be suitable to support the point loading from the props, which is kind of underneath, which leads us on to back propping. Is it feasible to back prop below? The floor below may well be occupied by a third party or restaurant that is currently open, so we need to make sure that we understand if we can back prop, and if we can't, then that leads us to other solutions. Lateral stability and the support of other structures. So we have an arch here. Will that be supported by the needling? If the wall is acting as a shear wall to provide that stability to the whole structure, so do we need to consider global stability as well as the local stability of creating this opening? Construction sequence and how the new beam is installed. What's the permitted working space? Are there other systems in place around it, which is going to make installation very difficult? Is there a specific construction sequence required due to site constraints or the permanent works sequencing? Permanent works as well. What does that look like? And does it consider that the temporary works will need to be used to install the beam? Because believe me, that does happen. Check for any services. Are there any, and are they live? Do they need redirecting or supporting in the temporary term? Exclusion zones. Are there any exclusion zones which would be required for this scheme? If we're loading the floor below with these additional loadings, then how much more load can that floor take before it fails? Hence why it's typical practice to have exclusion zones in these areas to reduce that loading. But there may well be exclusion zones associated with other temporary works nearby, so that needs to be fully understood. Allowable deflection on the structure. So this should be governed by the type of the structure and its use. So it's very important, as it's often the driving load case for the design of the system, to understand how much settlement or how much deflection are we permitting in this structure. Are we allowed to, is the structure allowed to crack, or is it does it need to remain in pristine condition? Are we supporting the vertical loadings only? And this links back to the arch here. So do we need to provide some horizontal support to that arch, perhaps, to put a tie across so that we're not we're removing that horizontal thrust load right next to what looks like it would be quite a skinny pier and an opening directly next to it. The overall stability of the structure with the openings created. So if this wall is acting as a shear wall of some description, then that global stability assessment may well be necessary. There should be someone reviewing whether you can turn the structure into that Swiss cheese kind of building, which I mentioned earlier, with lots of holes in it. And can they all be completed at once, or do they need to be split between floors so you can carry out the openings on that floor, then complete the permanent works, then you can start the next floor down, etc. And other openings nearby and interface between them. That's this last point links to the global stability assessment, really. And on some schemes, it is important that you have a separate method or a separate drawing just to say you can do these together or you can do these together, and there's a sequence of when things have got to be completed to make sure that we remain or the structure remains stable. There are other considerations that will be project specific, but if you plan ahead and start discussing these concepts and schemes, then the work should go nicely to pick up all those constraints. Okay. So now that we know the types of things that we need to consider, it's time to furnish our temporary works toolbox, imaginary one, unfortunately, with all these different ideas that we can have to utilize in our project. That way, when a particular solution or challenge or issue or challenge comes up, then we can already have in mind lots of solutions that we can run through that that would work and we can employ in that particular project. I was reminded the other day by a colleague of mine that a craftsman is may well have some really good and sharp tools, but if they don't know how to use them, then they're going to create something quite blunt and ugly. So as shown on the list here, there are several different types of propping and needling schemes that we can employ. Sometimes a mixture between them is most appropriate, but we're going to look at 7 today, which are most common. So this is more on the domestic side or domestic openings, smaller openings, which are quite common on the domestic side. We're talking about a maximum wall thickness of around about 230 mil, or double skin cavity wall, and openings up to 2.5 meters or so, that kind of size. The first example here is a no more prop solution, or a temporary lintel. It's a single tool that replaces the need for multiple acro props, saving lots of space on site and site prep time on the ground, etc. It's an off-the-shelf product. It's great for small-scale applications. It does rely on that masonry arching, which we discussed earlier. So it needs to be on a kind of a long wall. But it is, yeah, so it's quite handy in particular examples. Brick brace is a similar proprietary item. It's quite a clever system that effectively uses the technology similar to post-tensioning structures. So it's like a scaffold tube with fixings at regular centers. Those fixings have plates which go into the masonry vertical joints, which are then opened out with the plates, and which kind of compresses all of that bottom row and creates a deep beam. Essentially, it's quite a clever and neat solution. And now for the strong boys. So these props are for a similar application, really, as the no more props in terms of its use, as the prop head attachment is only good for a safe working load of 350 kg. So that's a factored capacity of 350 kg. So we're talking quite small scale here, and they're often used very close spacings because of that limited capacity. So we have a steel head plate attachment, which I've popped in there, and that's cut into the wall at regular centers and supports the brickwork. An example of this propping scheme is also shown on some of those pictures. The row of props closest to the wall has the head attachments on top, and that kind of cantilevers in to the wall to pick up that wall. And then the row further away from the wall is supporting the floor above to remove some of that loading away from the opening, and just the loading was only on one side because the floors on the other side of the wall spanned the opposite way. The propping was founded on some aluminium beams that then spanned over the floor just to put the loading back into the load-bearing wall. So we can see these the concepts of these illustrated here. On the left is a simple scheme where the props are supported on floors, and to the right where we've got a very weak floor alternative. Most often the loadings we get from strongboy props are low due to their low capacity, thus the propping down to an elevated floor is usually acceptable, providing that a proper load assessment has been carried out and we put some timber scaffold boards beneath. But understanding the floor spans and construction of the floors is critical for that, which links back again to that good SI. This system is also good because the props are all on one side of the wall. So when you come to put your beam in, then you've got one side of the wall which is totally open, and it's easy to just use your equipment, whatever you've got, to get the beam in. And if we review that against a typical sequence of installation, which is for all lintels really, it's the propping of the opening is installed to fully support the wall. And at that point, an opening is made to receive the new beam or the lintel, and this doesn't have to be the whole wall. It can just be a slot, just big enough to get your beam in, and then allow that beam to be supported by the pad stones, which are installed as well. Then once the beam and the lintel is installed and dry packed to ensure it's all ready to take the load, at that point, the temporary works can then be removed, and then the wall demolished. That's the process in a nutshell, really. Here's an example of that in practice. It's quite a neat solution there. And there's a competent team on site when you look at the drawing and you look at what's been constructed on site, and they're, pretty much exactly the same. That's a neat solution. So that's a very common practice: acro prop, strong boys, and some scaffold lacing to maintain stability. Okay. If we are putting some larger openings together, then this could be a thicker wall or higher floor loadings or something similar to that. We would employ something similar to what's shown here. So we've got larger needles. The needles are the horizontal beams which run through the wall and kind of needle through the wall. Those beams are size dependent on the load. And then on this particular item, we've got vertical props coming down at the support of every single needle. So it's regular supports down to a structure which can support the load coming through. The scaffold bracing doesn't have to go through the opening like is shown on here. Presumably that on this schematic, that's added afterwards just to provide a bit of stability, because when you're erecting it, there is no wall there in place, which is why we can typically put in a raking prop, such as shown on this solution here, just to provide that lateral stability. An alternative to providing a prop on every single needle is to have a header beam between the two props and to support your needles from those. And the centers of the needles remain the same, because that's really important that we pick up the structure at least 800 to 1 meter centers to maintain the support to the wall, so we don't get lots of loose brickwork dropping down. We're providing lots of regular supports, and then we can have a header beam all under those needles, and then some strong props either side to support those. That enables quite a large opening there, which may well be useful as a kind of goalpost solution to allow access or small plant to run through, etc. If we are propping an opening on a raised floor and the floors are weak, then we can employ something called reverse needling. This scheme takes the load from the wall, distributes it to the needles, into the props, and back into the lower needles, and then back into the wall, just like that, okay? This is a really great idea, as when we are working on structures and changing how it behaves, we try as engineers to try not mess around with the load path so much, because we're putting stresses on the structures which we don't necessarily know it's experienced before, which may well lead to cracking that we want to avoid. So if we can keep the structure behaving as it has been its entire life during this process of making an opening, then that's a great idea. And that's what this scheme is all about, really. So the propping from the floor to the ceiling is used, and that's just for stability, really, because we've almost got like a floating frame. So the propping is non-load bearing. It's just something strong enough to tie to. It doesn't have to be a prop if there's something nearby, scaffold or something. It's just to provide a bit of stability. Okay, so that's a really neat solution, reverse needling there. Okay, now let's look at needling with larger beams and with a pinned wall. So this is a scheme where the loads were really high as we were supporting the whole facade, because the opening was all across the shop front there. The area beneath the propping was also required to remain open to enable the demolition works. Therefore, I developed a scheme that had props at approximately 5 meters apart. Then we had larger needles at 2.5 meter centers, and then back-to-back channels spanning between the needlings to pick up the needles to pick up the wall, which you can kind of see here a bit closer. So the PFCs are essentially strengthening the bottom line of that wall and are designed to span between the larger needles. A sleeved rod is inserted through the wall, which then ties the back-to-back PFCs together, a little bit like that, which we've got a close-up of those needles and the pins. It's important that the sleeve is used, as the rods themselves, they've got quite a low bending capacity, and this is quite a high load in a thick wall. So we use those kind of sleeves over the rods just to provide that extra support in bending. Due to the size of the loadings and the quite awkward site constraints, it was necessary to go with a bespoke fabricated steel solution. And this PFC pinned solution can also be used to limit damage in the wall. So it was something that the wall was quite precious to the client. We proposed lots of different solutions, and they felt that this solution was the most appropriate to limit how much damage there was to the wall. So we could maintain as much as the fancy stonework wall as we could. Next one here is the Pinaford stool method. So this is a method often used for casting an in-situ beam inside a wall over a proposed opening. The illustration that we've shown here has been taken from the Temporary Works Toolkit, Part 10, which is published by the Institution of Structural Engineers. And it's great. They've got a series of lots of articles, and this one is primarily aimed at assisting the permanent works designer with the temporary works issues. So this sequence, it breaks out in stages how to form a new lintel in an existing wall, and the sequence is to break out pockets in the wall and insert some little stools, which are usually steel box sections or cut down steel eye sections. And then once the stools are in and then dry packed, i.e. they're ready to take the load and support the structure above, so it's nice and tight, then the lintel channel, which is the extent of where the lintel will sit, that is then created to form a large slot along the wall. That slot is then used to form the rebar, and the new lintel is placed inside, i.e. all the steel fixings is carried out. Shutters are then placed around the slots and the concrete is then cast. That top of the beam, that is important that it's dry packed so that it is tight to the soffit to ensure that it's bearing against the top of the wall and there are no air pockets at the top during that casting process. Once the concrete's cured, then we're all good and we can remove the wall underneath, and that's, hey presto, that opening has been created. I've got an example here of a design where we used the Pinaford stool method during the Low Cross project in East London, and we used these steel stools that were designed to sit inside the new lintel and therefore not clash with any of the reinforcement that was used for the new beam. And the process was, as you can see here, to make the pockets, install the stools, then you form that slot, which then enables you to put all the rebar in that's going to form the lintel ultimately, and then cast the concrete, let it cure, dry pack, make the opening. It's quite a neat solution. Oh. And it's a detailed view that I've put in here of the stools and how they sit around that reinforcement. It's really quite a niche method, but it's a very handy one to know because on certain challenges or certain requirements, this solution is just perfect. In a similar vein to the Pinaford stools method, we can use back-to-back PFCs as little stools. So they are very short stubs and they're back-to-back, and they allow the installation of precast lintels because they sit in that opening that the PFC stools channels provide. Those channels are a perfect shape for that, and they are done one's like handed, so they're done one side and then the other, and it's a great solution if you've got a number of precast lintels to install because you can do one side at a time. So I'm going to show you a typical opening and that sequence of the back-to-back PFC stools method. So we have a typical opening here, and you can see the load interaction zone and the proposed location of the stools shown in those three hatched blocks. So they are short stools, okay? They're just short sections. If we take a section through this, we can see the sequence of that installation. So the sequence is similar to the Pinaford stools method. However, as this is a sequence that allows multiple lintels to be installed side by side, one side is usually done first, which then is all completed and totally load bearing, which then enables you to carry out the other side. And this ensures that the wall receives as much support as possible throughout the works there. And here's what we do. So we break out the pockets and install the stools on one side. Then we dry pack the stools so they're nice and tight and load bearing. Once they are load bearing, that means that we can form a slot on one side of the wall and install one of the lintels. We dry pack that lintel, make sure that that lintel is now ready to provide support. which means that we can do the same on the other side of the wall, okay, until we've got full support along the whole wall, at which point we can then sign off the permit to remove that wall top down, and then we have our opening. It's a really quite neat solution. The ends of the steels are usually just cut off or boxed in. But as I say, it's the Pinaford stool and this back-to-back PFC stool is quite a niche methodology, not very common, but on certain situations they are a really neat solution. Okay, the next solution is going to be explained through the use of a case study, and that's the India buildings in Liverpool Liverpool city centre. The project was in a really interesting building. It was a double-story basement and a number of floors built in 1931, I think. The scope was to redevelop the structure in a cut and carve type. So we were using creating many holes in walls, so it's required lots of different needling schemes. The design brief in this area was to create an opening to a new lift shaft, which was being constructed. And the existing floors either side of the opening were also not at the same height, which really added to the further complexity. There are also embedded steel beams within the walls, and due to this construction work that was going on, it was agreed that the best option to go with was to have a needling scheme which could be constructed and steelwork installed all from just one side. This detached this particular wall opening activity from the lift shaft work on the other side of the wall and effectively removed the link between the activities on the critical path. So there was a bit more going on than just this one opening on this project. And we've got the solution here. So this is called scissor propping. The concept of that is that we have needles similar to the reverse needling solution that we saw earlier. So we've got a needle at the top and a needle at the bottom, and that allows the load to come down through the needles, through the propping system, and then back to where the load was originally. So it's a solution which is, it's all being resolved within one floor, which detaches it from what's going on the floor above and on the floor below, providing we're controlling what those loadings are, or we've considered those in our analysis. The difference between this and the reverse needling is that the props are all on one side. So we've got a prop very close to the wall, which is acting in compression. It's being squashed down. And then we've got a seesaw effect over the top and bottom of that prop. And to restrain that seesaw effect, that overturning over that fulcrum, then we need a tension tie at the back. It can be done with a rod, but we often employ structural members like this maybe system here, just to provide a little bit more robustness. So on this project at Liverpool, at the India buildings, we used the proprietary solution, which was maybe system 160 in this particular case. And that was used to provide that robust frame that could also take the loadings from the structure. There was an existing opening within the structure that was allowed for, which you can see in that white box. So what we did there is we just brought that bottom member down. It's also important to think about the installation and how the new structure is going to be installed. So in this case, we allowed for the new beam installed to be done with a genie lift, to have a larger opening in the middle so that the genie lift could go in with its forks and pick it up and pop it in. Finally, the system allowed work to continue within that new lift shaft, which is really important to separate those two items off the critical path and allow them to progress independently. And then we've got the structure in reality there. So you can see the main load is going from the top needle through the vertical props and then back into the bottom needle. There is a strut which comes down all the way across the back. That's working in both tension, but it goes down to the floor below, and that enables the system to be constructed because it's essentially a floating support system. There needs to be some form of support there to enable you to build it. If it's on a relatively flexible floor, then as soon as any load goes down to that flexible floor, the floor deflects, and then the load then gets transferred to parts of the stiffer structure, which is the wall adjacent. So it works quite nicely, really. That are all they are all the solution, or the most common solutions to have in your toolbox. Hopefully, they're going to help you out on your projects going forward. I'd like to hand you over to Richie, who's going to look at a worked example, taking us through some loadings on a particular project. So over to you, Richie.
Yeah, it was a project I worked on a few years ago. It was just down in London, and they were making an opening in a wall in a basement. So they need propping and needling for that. But as Josh says, propping and needling is some of our bread and butter. We do it day in, day out. I'm yet to find one that's identical to one I've already done, but most of them follow the same broad steps. As Josh says, the basic idea is that the load from the wall goes into a set of needles, and from the needles, we transfer that load into props, and then hopefully down to some suitable foundations. These foundations can be the scissor needles or the reverse propping that Josh was talking about, but normally into either a ground bearing slab, some ground, or something along those lines. So in my experience, I have seen a concerning number of examples where people just have not designed these propping systems adequately or taken propping seriously. Some of them have been quite horrendously dangerous. To be honest, on the left is a residential job in London, quite close to the one that we're talking about. They had already installed remedial props in this case when I came to look at it in the first place. But as you can see, they've got a line of needles. If Josh pushes a button, you'll see where the load should have been. And in there, there used to be a line of needles going across there, but they've put them too far apart and a big chunk of the wall fall out and lots of needles fell over. It wasn't going well, so they called us to come and have a look, and we had to redesign the whole thing and get a lot of remedial props in there. The second one is on a larger scale project in North Wales. There was a cut and carve job. There's some strong boy props, and as we spoke about earlier, they can only take about 350 kilograms, but this was supposed to hold up a major load-bearing wall in this building, and an eagle-eyed TWS from the adjacent job noticed that that was not going to hold up that wall if they made that opening. But you can see they'd already started the works, so it was good that he spotted it when he did, otherwise that could have ran into some serious problems. But on to what I'm going to actually be talking about today. I'm going to take you through a set of calculations for how we would typically design propping and needling jobs for a wall opening. The first thing that we have to calculate is the loads on the new lintel level. So the loads that the needles will actually be taking, and then the lintel will be taking afterwards. In this example, just imagine that we're making a wall opening in a masonry load-bearing walls. We're not at the edge of the structures. It's a masonry wall that's in good condition. We're not going to look at these extra things that add levels of complexity to the job. In this solution, we spoke about load triangles and interaction zones before, and the natural arching of the masonry that takes the load away from these triangles. So when you're doing this, all you have to consider is the loads that are inside these triangles when it's in these good conditions. And then these loads in the load triangle, which you can see there at 45 degrees, we take into account the actual weight of the masonry of the wall. And in the interaction zone, we don't take into account the weight of the masonry. We only take into account the loads that are applied from floors or things like that. If you go back a bit, Josh, before you move on, the actual opening was about 4 meters, and the load triangles are a bit longer than that there. just an extra 10% or so, so that we can take into account the arching over that as well. You can move on now, Josh. Yeah. In the load triangle, so the load triangle is at 45 degrees. The floor loadings in the load triangle, you have to take into account the live load, any other live loads you've got going on, if there's any plant moving around in that load triangle. In this case, there is a floor at 500 mil above where we're putting in the lintel. So we had to include floor loads there. There was a live load in it, although in most cases we would recommend an exclusion zone being there while these works are carried out. Not vital, but best practice to just make sure that no one's walking about on these floors while these works are going on. In other cases, you have to take into account environmental loads. This was all inside, so there's no snow loads or anything like that on this. And of course, the dead load of the floor needs to be taken into account. Other loads are point loads, openings, beams. In this case, there was none of these, but any partitions would add on additional loads. The openings, if any corners of openings are in the load triangle, you have to account, because the arching effect brings the loads from that opening to a point load in the corner, and that loads the system from there. So that's the different kind of loads in the load triangle. In the interaction zone, you've got mostly the same kind of loads, but the loads are halved. So instead of having the full floor loads, you have half of the loads, because outside of that direct loading loading triangle. And again, you've got the partition loads, openings, and beams. You have to take these into account. They're the things that can really cause some complexities to arise when you're doing these designs. But in this, you still have to take into account the openings in this area where the corner is applied will load your lintel level. If the opening corners are outside the interaction triangle, you don't need to take them into account. It's only when the corners are actually in the interaction triangle or the load triangle that you have to take them into account. So the loads on the lintel that we're actually talking about. So as I said, masonry wall and floor loads are all we're going to be talking about in this. So basic things from the structure. The wall was quite thin, 214 mil. We've allowed for an additional 500 mil of masonry straight above the lintel, just because that brought us up to the floor level. So before the load triangle kicked in. The density of masonry, it wasn't just typical masonry, 19 kilonewtons per meter cubed. So the load from the masonry, you've got the height of that triangle times by the density of masonry times by the thickness of wall, and it gets you to about 9 kilonewtons per meter, and that is a triangular load in the shape of the load triangle there. We also had a UDL from the 500 mil of masonry we took into account. We add that on as just a safety buffer in this situation. And of course, we've got the loads from the floor as well. So we've got live loads on it. People were still working upstairs, so we had to take that into account. Dead load of the floor, just a typical timber floor, so just 1.5 kPa. And the span of the floor was, it was 3.5 meters in both sides. It worked out as 3.55 meters loading the actual wall that I was looking at. So the UDL is from the floor loads is a lot higher. It's 12.5, and that loads the whole lintel. If that was in the interaction zone at all, that load would have been halved. But the way that we set up this load triangle, it was all in the load triangle at the very bottom. So it was the full 12.5 kilonewtons that was loading it. It is quite important to note that these loads that we're taking are unfactored loads, because we're working to permissible stress rather than limit state, because we're going from BS 5975. So we're just comparing unfactored loads to permissible capacities. Move on. So in the design state, now that we have the loads, we can apply them to the level of the lintel, and this is where the actual design process comes in. You have to determine how many needles you're going to need to support this. In this case, it was the spacing that was the main determiner. So these are at about 910 millimeters apart. If you had one more, they'd be close together that you couldn't work properly. If you had less, they'd be too far apart. So we went with the 6 needles like that. From this loading diagram that you can see that the maximum load on the needles was 25 kilonewtons, which is a substantial load. No strong boy system could take that by itself, so it was definitely the propping and needling system was used. From in between those needles, some masonry might fall out. That is a residual risk because the spacing is about 900, and obviously that's bigger than a single brick. So moving on to actually checking the needles, we've positioned the props asymmetrically to allow space to work in between the interior prop and the wall. This changes the loading on the needle slightly, but it was more than worth it so that we can have that extra space. So we design the needles. In this case, it was just square hollow sections. And we were considering bending, shear, and deflection. The deflection was a critical case in this by a long way. The deflection drove the entire design of these needles, and we limited deflection to 3 millimeters, although it would have been limited to span over 500 on the masonry anyway. But the 3 millimeter limit was to avoid the masonry cracking from above the lintel level. Now, if we go on to where we're designing the props, because we loaded it asymmetrically, the props have one taking a greater load than another. From this, it wasn't much of a difference between the props. They're not hugely out of sync. So it was about just under 15 kilonewtons on a single prop, and the height was 2.75 meters. So a single acro prop for each side of the needles was more than suitable for what we needed it to be. And then after that, if we follow the load down, you get to the ground level. On this case, the inside load was just on a concrete ground bearing slab. Because the loads are so small, 15 kilonewtons, we could tell that that was going to work anyway. But on the exterior load, it was just into it was into old garden soil. There was a roof and extension built above that, but it wasn't taken into much loadings. So we removed the topsoil and then we put down some sole boards to make sure that we had adequate bearing. So we just considered that the bearing at the bottom of an acro prop would give a pressure of about 500 kPa. If you put down a couple of sole boards, you get that to within an acceptable 150 kind of range. That is the basic process for how we do it, and some numbers to go with it. As Josh mentioned, you might notice I stole this picture from him as well. Sometimes lateral stability is a huge thing. As the props that I was designing were all inside, it didn't really matter much for lateral stability going in that way. There wasn't any big plant going about that could knock the props, no wind loading. But in other cases, you do need these triangulated props to help with lateral stability. And then, of course, once the propping is safely installed, you can break out the wall and put in the lintel. And I think that's it from me. So I'll hand it back to Mr. Josh.
Thank you, Richie. That really takes us to the end of our webinar today. There's loads of stuff out there on propping and needling because it is quite a common practice event on all sorts of sites, from the domestic to commercial. I've just put a few items on there. The Temporary Works Forum is a really good resource. Lots of free information on there. That's really good. There's Temporary Works publications by the ICE, Syria guides, and iStruct noted there. Richard mentioned BS 5975. That is the go-to British standard for temporary works, permissible stress design. And that's the majority of that British standard, which hasn't been superseded by Euronorms. The majority of it is covers procedural control of temporary works, which is a whole nother subject for a whole nother webinar. We've got videos on that on our YouTube channel.
Yeah, I think we've done a few webinars on that before.
Definitely, yeah. Thank you for attending and listening. And hopefully you've learned something that could help you out on your project in the future.